Hello, it's the quartic formula here. This video is not a calculus lecture. This video is, just a video I decided to do for fun and to do something a little different from calculus today. So today we're actually going to be proving one of Euler's most famous entities, e to the I pi is equal to -1. So this one is pretty cool. I'll also be proving more general formula with this. So you'll see what I mean in a second. So for this video, you should know what a Maclaurin series is, and also you should know at least a little bit about complex numbers and at least know what I is. So let's start with our scalar series. So we know that cosine of x is equal to this series right here, and this is the Maclaurin series. So if you plug in 0, so let's actually go and write this out. So we plug in 0, and we get x to 0, which is 1. 2 times 0, x to 2 times 0, which is 0, which is 1. And then that is also 1, and that is 1, so we just end up getting 1, because 0 factorial is 1. And then we plug in 1 for n, the next index, and we get -1 over 2 times x, because factorial is 2, times x to the second power. So minus x squared over 2 factorial do 2, so we get -1 squared is 2, is 1. -1 to the second power, it's not 2, -1 to the second power is 1, over 4 factorial times x to the 4th, so plus x to the factorial, and we're going to get negative x to 6, we can take default pattern, and so on. So you should be familiar with these series. I'll go ahead and write the next one, which is sine. And we'll get -1 to n plus 1 factorial. Again, times x to the 2n plus 1, which gives us x. We plug in 0, we get -1 to the 0th power is 1, over 1 factorial, which is 1, times x to the first power. x1 we get -1 over 3 factorial, times x to the 2 times 1 plus 1 power, which is 3. So x to the 3rd power over 3 factorial. And we follow the pattern as well, just like I did with cosine. We just keep in terms of the summation. We'll get obviously an odd polynomial. And finally, we will have e to the x in this Maclaurin series. So remember that these Maclaurin series, these series converge for all our numbers. So this is actually an easy one. X to the n over n factorial, which is equal to 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial and so on. Great. So you might be thinking, okay, great, what does this do to prove the identity? And you'll see what this actually does for us in a second. So I want you to take a second and actually take in these series, take in the fact that this is what cosine looks like, it's an even function. This is what sine looks like, it's not a function. And this is what e to the x looks like. And we'll be starting with this, and we'll actually get an interesting result. So, I've taken that in for a bit. Let's take let's look at e to the x. So, we want to prove that e to the I pi is equal to -1. Well, how can we do this? Well, we know that obviously e to the I pi is equal to I pi, so we plug I pi into e to the x, we get e to the I pi. That doesn't do much for us. So, let's consider plugging it into this. So we can try to find the pattern here and maybe reduce this to a simple form. So let's plug in I pi for x, right? Because this is x, so sorry, not I pi, but I to the x. We'll get a more general formula for e to the ix, and then we can just plug pi in for x. So to illustrate what I'm trying to say, let's go ahead and take this. Let's start plugging in that's too much. Let's start plugging in ix. To get a more general case, because we want to prove that e to the I pi is equal to -1, but doing this in general might be a little easier. That way we don't even have to restrict ourselves to e to the I pi. We can expand that to maybe e to the I 2 pi. Well, that's trivial, but other values in there. I think I picked the most trivial example possible with that one. That's funny. Okay, moving on from that embarrassing episode. Let's continue with my reasoning. So, we'll just do it to the degree of this stuff. Actually, I might go one more degree to illustrate it. Illustrative point. Actually, no, this is perfectly acceptable. Okay, so we get here. Now, think about it like this. We know what I is, right? I is a number that when squared yields -1. So it's essentially as a complex number, it is a, which is 0, plus b, 1i. So 1i, or I. It's a number that when squared yields -1. So great, we have I here, we have I here, I here. So let's start thinking about it. So obviously this equals, well, so far 1, right? Because that doesn't change. Plus ix, again, nothing changes here. We're going to keep using parentheses, and actually, no, we're not. We're not, and we'll see why in a second. Ix. Remember that ab squared is equal to a squared b squared. So in this case, we see that we have a squared, which is I, and you square that and you get -1, and x squared. So you get -1 x squared over 2 factorial. So negative x squared over 2 factorial, right? Because you're only squaring up here, this stays the same, the denominator stays the same. So we'll check this out a little better. It's ix minus x squared over 2 factorial. And now, if we have I, which you do, like I is square root of -1, right? So square root of -1 times the square root of -1, square root of 1 over I. This is just -1 times I, which is -I, right? So we all know that I cubed is equal to -I, right? So we have negative I x cubed because I cubed is -I and x cubed is x cubed. And the denominator stays the same as always. So we have that. And I don't know if you see this yet, but we're going to have to do some factoring and actually you'll get a very interesting result. And obviously this continues, so we don't just stop. When we plug in ix to, for x, we don't actually stop. You know, you can think about it as like we do it forever, but I'm just writing this because I can't actually go and plug in ix for every single term in the Maclaurin series of e to the x. That would, you never get it done because you can't do an infinite amount of tasks. Okay, so we know that I to the fourth is just -1 times -1, which is 1, right? So we get plus x to the fourth over 4 factorial, and so on. And so we get, if you follow this pattern and you actually plug that in, if you actually do ix to the fifth power over 5 factorial, you'll see that we end up getting so we actually end up getting the plus minus. Well, how about this? We end up getting something rather interesting. I'm trying to think of how to best phrase this. Okay, so let's actually move some stuff around. So I don't know if you see it yet, but we have so far 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And if you follow this pattern, you actually see that we end up getting minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and so on. But we also end up getting plus I x to the 7th over 7 factorial minus, so minus plus, yeah, no, it should be minus, minus plus x to the 8th over 8 factorial, and so on. So what we're getting here is we're getting something that looks a lot like sine and cosine being added together. And that's actually exactly what we're getting. So if we kind of group this and see if this process goes on, if we group these two things, x to the 8 over 8 factorial plus that. And we can add that to that. So x minus ix third over 3 factorial plus ix to the 5th over 5 factorial minus ix the 7th over 7 factorial, and so on. Then we get something interesting. But this is cosine right here. Remember what we reviewed earlier? This is cosine. This is the Maclaurin series for cosine. Now this doesn't look like sine. Yet. So what we're going to do is, it does look like sine, but we have an I in there, right? So if we just kind of brought that I out, it would be sine. X minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So if we just bring out that I, it will be sine. So let's go and bring out the I. So we can go by this as cosine of x, because we know this is cosine of x, right? So if we bring an I out up front, just by factoring, we have I times x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on, which we know this is sine, so it's really just plus I sine of x. So we just showed, and this is really, really, really cool, and this is actually my favorite identity in mathematics at the moment. It does change. So I guess people say like their music changes like based on the week. Their music taste changes based on the week. My mathematical taste changes based on the week. No, but it's always been one of my favorite identities. We've just shown that using e to the x's Maclaurin series expansion, we've just shown that e to the x is equal to the cosine of x plus I times the sine of x, which is actually really, really incredible. This is like a really, really interesting identity. So we're just proving it using the Euler series, which is like really cool. I don't know. I get really excited about this one. And so let's go ahead and use this to prove our identity. Yeah. So not only are you going to be able to prove that e to the I pi is equal to -1, we also just found a general formula for e to the ix. So this is not e to the x, e to the ix. So yeah, e to the ix is equal to this. Sorry, I neglected to put the I there. So e to the ix is equal to the cosine of x plus I times the sine of x. My mistake. Yeah, I thought I put the I there, but apparently I didn't. Alright, so we then can plug in pi for x. So e to the I pi is equal to cosine of pi, which is trivial, plus I times the sine of pi, also trivial. Great, so we've reduced this seemingly non-trivial problem to actually a quite trivial problem where we just take the cosine of pi and the sine of pi and multiply the sine of pi by that. Right? So that means the cosine of pi is -1 and the sine of pi is 0 plus I times 0. Well, I times 0 is 0. -1 plus 0 is equal to -1. So e to the I pi is equal to -1. And you can put a little QED there. A little fancy about it. Oh yeah, for those of you who don't know, QED is abbreviation for Latin quod erat demonstrandum. Demonstrandum. Sorry, I'm getting a little bit of Czech accent in there. Which essentially means which was to be demonstrated, which was to be shown. And so that's commonly put at the end of mathematical proofs. This isn't like, I mean, it's sort of a proof. And you could also see a white box for this, or you could see, well, my chalk is white, but I filled in black box for this in a lot of textbooks. In fact, I know that Munchers does this. Munchers does topology, and I know that Sheldon Maxwell's linear algebra done right does this as well. Anyway, yeah, so we just showed this is true, and I think that's really cool. It's my favorite, one of my favorite entities mathematics. I like the general form right here better, but yeah. So I hope you enjoyed. I know this one was a little shorter. I'll be back taking practice videos most likely tomorrow, if not the day after, probably Friday night. But yeah, thank you for watching, and please don't forget to like, comment, and subscribe.